Hey everybody. So yes, I am here. You get early morning, Patrick. It's still quite early here. Um, so anyways, yeah. Excuse me, I've had a bit of a cough. But yeah, so office hours. It's a new thing, right? But this is good too. So I saw some people. I'm gonna keep a little list over here. Excuse me. If anybody does have suggestions for topics, like I'm always on the lookout for this. So this is something that would be good. So I'm going to even open a little Google Doc here to put some of this down. So somebody did ask about algorithms. So I do have stuff on how do you say Dijkstra. I think that's how you pronounce his name, Dijkstra. Um, So Dijkstra, I think that's how you pronounce it. I know I've got at least one graph theory video on that. Um, I don't go super in depth, but I think it gives the gist of it at least. But I will um, jot down the other one as well because I don't think I have anything on that. In fact, I'm not even familiar with that one. I'll Let me copy those. Okay, so again, if anybody has questions, ask or suggestions, or I may just keep this short. So let's see. And I don't know. How is everyone? This is the problem with streaming, right? You got to be a bit of a personality, and I don't know that I've got the personality to carry a nice long live stream, or maybe not the personality is the right word. Maybe just the interest. So, are we just hanging out? If not, I'll turn my camera off and just chill out. And we'll see. Maybe there won't be any. Let's see. So, any recommendations to start relearning basic math up to physical chemistry? Yeah, that's quite a lot, right? So, I mean, I guess it depends on what you consider basic math. Um, Nothing in particular, really. I would say just it depends on where you are. It's really impossible to answer just based on one sentence. So, I will say there's obviously gobs of good free resources out there. And chemistry gets complicated. I only took one college chemistry course, and it was not easy. So that I will leave to the other experts. But okay, so we'll see. I know this is early and random, especially for people here in USA. So, all right, well then, let's just see what happens here. Okay, so yeah, there was a question on partial derivatives here, so let me do one. Oh man, maybe I should try to get a look like I didn't just wake up here. 1 second here, let me just get my screen set back up. I've got way too many things open at the moment. Okay, so this looks good. So I guess, are you just mainly looking for the mechanics of it more than anything? Is that you know, what you're looking for? If so, we can certainly do that really quick. Um, that's at least the easier part, the mechanics of partial derivatives. Um, yeah, so the Taylor polynomial, there's something called Taylor's remainder theorem, AMB. That's what you would need to use on that one. So maybe we can look at that in a second. It's not trivial to use. I mean, it's not terrible. I would have to look over. But yeah, you're using Taylor's remainder theorem is what you would use for that. Okay, so just the mechanics of partial derivatives. I don't know. I'm trying to find. Let me take. Um, so let me think of an example. And I'm going to make an example in 3 variables just because I think it's. Um, I think 3 variables is clearer. And then maybe I'll do a more complicated example as well. Okay, so if you're the mechanics, the idea is so the notation, right? So in here we've got our 3 independent variables x, y, and z. So we could have our first partials, the partial with respect to x, the partial with respect to y, excuse me, the partial with respect to z, and that's how you read each one of those. The partial with respect to x, to y, to z. And the thing that I think about when I take the derivative, when taking derivative, So for example, when I take the partial with respect to x, I'm going to treat, and I know they say this, but let me illustrate, treat x like a variable. I'm going to treat x like a variable and y and z like constants. And I wrote yz. What I mean to say, and I think I said it correctly, I'm treating y and z like constants. So for example, x squared, y to the third, z to the fourth. If I take the partial with respect to x, okay, so in this case, I'm viewing my y to the third and my z to the fourth like constants. So to me, in my head, this kind of looks like, it's kind of like having x squared times 8. You know, I've got x squared times some number. And of course, I could even write that as 8x squared. Whoops. So the idea is, and let's not even write that out. So the y to the third and the z to the fourth, those are just like constants. So we don't really do anything with those when we take the partial with respect to x. I just take the derivative of x squared, and that's just going to be, well, 2 times x to the first. And then we could simply just rewrite that as 2x. And then notice I left the y to the third and the z to the fourth alone. Because again, I'm treating them just like a number. Right? It's the same idea as if I just had 8x squared. If I take the derivative, a lot of us would jump straight to the solution and say, oh, it's 16x. But really what you're doing is you're leaving the 8 alone, right? You're leaving the constant alone, and the derivative of x squared is just 2x. And then we combine them at the end, 16x. So you're doing the same thing in this case. It's just that these variables are now treated like constants. So you leave it alone, and again, the only part you're taking the derivative of is the x squared part. Okay, so let me know if you're out there, oh my, and if this is making sense, because I'm basically talking to you for the moment. So the same thing here. Let me rewrite my original one, and then tell me if you want to see something more complicated, because obviously this is the basics. So if I go to take the partial with respect to y, I'm now treating the x to the second and the z to the fourth. Those are like my constants, right? I'm not doing anything with those. So the x squared and the z to the fourth, just leave it alone. So the only thing I'm taking the derivative of, okay, I got your thumbs up, oh my gosh, thank you. So the only thing I'm taking the derivative of is that y to the third. Okie dokie, well, the derivative of y to the third, that's 3y to the second. And again, now I just sort of clean it back up is all I do. So, right, we put our constants out front, there's my 3, and then again, I'm just going to re-alphabetize. So there's my x squared, there's my y squared, and there's my z to the fourth. Okay, so one more time, x squared, y to the third, z to the fourth. So again, if I take the partial with respect to z, now I'm going to leave the x squared and the y to the third alone. Those are like my constants. And if I take the derivative of z to the fourth, well, that's going to give me 4z to the third. So again, I'm just touching the sort of the z portion of it is all I'm doing when I take the derivative. And in this case, again, I'm just going to rewrite it for, I'll write my x squared first, my y to the third next, and my z to the third again. So that would be all of the first partial derivatives. We would say we found the partial with respect to x, the partial with respect to y, the partial with respect to z. Now, if you wanted to, you could start taking second partial derivatives. So for example, suppose I wanted to take a second partial derivative. So I'm picking one at random. So this is a second partial derivative. I could write f of y, a little f sub y x, and what that means is we're taking the partial with respect to y, and then with respect to x. Well, we figured out the partial with respect to y. That's what we did a second ago. We said that was 3x squared, y squared, z to the fourth. So 3x squared, y squared, z to the fourth. So I could do it one more time. So now I'm just taking the partial with respect to x. So again, I'm focusing in on the x squared part because everything else in my head is just a constant. So if I wanted to, I could even write the 3y squared z to the 4th out front. And then if I take the derivative of x squared, well, again, that's just going to be 2x. And again, I could clean this up. So 3 times 2 would be 6. I'll leave my x alone. There's my y squared. And there's my z to the 4th. So that would be a second partial. That would be the partial with respect to y, and then with respect to x. And kind of an interesting question is it true? So suppose I take the partial with respect to y and then with respect to x. Would that be the same thing as if I took the partial with respect to x and then with respect to y? Does that hold true? So that's something that wasn't even asked, but it's kind of an interesting question. Excuse me for a second. Sorry about that. So that's an interesting question. Does it matter the order in which you take partial derivatives? And the question is, well, again, I guess I asked the question. Excuse me, I'm sorry, I have to eat something. I'm sorry, you have to listen to this. So in general, the answer to this question is no. Sorry, I'm going to write this out. My apologies. So in general, the order in which you take partial derivatives will matter. So it's not true in general that they'll always be equal. But in a lot of cases, they will. I should remember this. It's been a minute. I believe this is Fubini's theorem. It should be Fubini's theorem. Almost positive. You can double check that. Okay, so oh my gosh, does that work? Does that make sense? Would you like to see a more complicated example? Or does that, sort of work for you initially, sort of get you going? And there's some interesting geometric interpretations as to what a partial derivative is doing. Right, so that's one other thing that's interesting. So in just 2D, right, we've got x and we've got y, and we've got some curve, some function. It doesn't have to be continuous, but let's make it continuous. Now the idea is when we talk about a derivative, right, we're talking about sort of a measure of the steepness. One complicated one would be good. Okay, perfect. I will do that. So just to remind you too, so in 2 dimensions, when we take the derivative, it's just a measure of it's sort of a measure of the steepness of that tangent line, is one way to think about it. But the issue is, right, in 3 dimensions, when you start doing stuff in 3 dimensions, how do I want to label x, y, z? When you start labeling, when you have like a surface in 3 dimensions, because now that's what you're going to get. If you take some random point on that surface, there's sort of, it's like standing on the side of a hill, right? In 2 dimensions, right, if you're sitting on this little point, the top of the hill in 2 dimensions, there's only one way to go, sort of left or right, and that's why the derivative, there's only sort of a single derivative. There's only that one rate of change if you go that direction is the idea. But if you're sitting at a point on a surface, right, there's sort of lots of different directions you could go. And maybe in one direction you're going uphill, and maybe in another direction you're going downhill. And that's what that partial derivative is computing. It kind of gives you the slope of the tangent line if you go in that direction. Or maybe it says if you go in this direction, it's going to give you the slope of the tangent line. So maybe if you go off this way, right, it says you're going uphill and it's pretty steep. And maybe if you go some other direction, you're going downhill, but it's not as steep. And the partial derivative with respect to x and with respect to y, they're looking at a certain direction. They're looking like parallel to the x-axis or parallel to the y-axis. Ultimately, you're going to get into directional derivatives really soon. Yeah, the partial it gives you the measure of the steepness in a certain direction is what it does. It gives you the measure of the steepness in a certain direction. Again, here there's only sort of one direction, right? You just sort of, you sort of are traveling left or right. In that case, it's one-dimensional. But again, if you're, imagine if you're on like the side of a cliff or something, you could go straight up the cliff. If you're on the side of a mountain, you could go, straight up. That's steep. You could sort of go along the edge, right? And then that tangent line would have a slope of 0 because you're sort of just walking around, right? You're not going up elevation or down elevation. Maybe I want to go down, sort of downhill slightly. That would be a different partial derivative. So that's the idea. This partial derivative, again, it's just giving you the measure of a steepness in like all, you could face any one of 360, degree different directions. It's going to give you all of those. Okay, sorry, but that's important, right? That's the stuff that's important, is being able to interpret it. And that's all you're doing. You're just taking that notion of a derivative, that measure of steepness, and you're just applying it to a more general setting. And when you get to, again, directional derivatives, it'll do that yet in a more generic way. Let me throw one in here with some trig, just for fun. So 4 times cosine of, excuse me, we'll say x, oh my god, x times y to the 5th plus, let's say, z to the 3rd. Okay. So we'll do all the partials, the partial with respect to x, the partial with respect to y, and the partial with respect to z. So this one's slightly more complicated, not too terrible. Hey Jose, apparently I am live. Yeah, you're most welcome. I'm glad I could help you. Okay. So I'm going to take the partial with respect to x. So again, in this case, the only thing I'm treating like my variable when I do the partial with respect to x is my x. So everything else, my y to the 5th and my z to the 3rd, those are going to be like constants. Okay, so I'm just treating those like numbers in my head. Okay, so when I go to take the derivative, I'm going to have to use the chain rule first off. So I'll leave the 4 alone. Okay, so the derivative of cosine, we know that that is going to be negative sine. So by the chain rule, we leave the inside stuff alone. So there I am leaving the inside stuff alone. But now we have to multiply by the derivative of the inside stuff. Okay, so now I'm just using the chain rule. So now I'm just focused on the stuff inside the parentheses. So now I'm taking the derivative of the stuff inside the parentheses, but I'm remembering that only x is a variable. Only x is a variable. Okay, so when I look at this first term, it's like having some number times x. This to me looks like x times 10, or 10x. The derivative of x times 10 or 10x is just 10. It's just the number. So when I take the derivative of the x times y to the 5th portion, let me erase all this so it doesn't get too cluttered. When I take the derivative of that portion, x is the variable, y is the constant. So the y to the 5th is going to just come along for the ride. Now, z to the 3rd, again, that's just a constant. It's like having 20. Well, the derivative of 20 is just going to be 0. So by the chain rule, the derivative of the inside part is only going to be that y to the 5th. So obviously we could clean this up a little better, make it a little more compact. So let me write this a little nicer. So that's going to be times y to the 5th. And then just let me close off my brackets. And of course, I would rewrite this, maybe negative 4 y to the fifth times sine of xy to the fifth plus z to the third. That would be my first partial. Or excuse me, my partial with respect to x. And let me do the other ones a little faster. Again, feel free to post a comment if it's good or if it's bad. So I'm going to do the same thing. Let me clean this up a little bit. So now I'm taking the partial with respect to y. So y is going to be my variable. In this case, I'm treating everything else like a constant. Same thing. So we'll have to use the chain rule. I leave the 4 alone. The derivative of cosine is going to be negative sine. We leave the inside alone when we do the chain rule. And now I have to multiply by the derivative of the inside. But again, I'm treating y like my variable. X is like a constant. So x is just going to come along. It's just like a constant. The derivative of y to the fifth will be 5y to the fourth. And again, just like we had a second ago, the derivative of z to the third is just going to be a 0 because, again, it's just a constant. Okay, everything's so far so good. Perfect. So, okay, again, you could just clean this up. So I'm going to erase this part at the end because, again, it's just 0. So what does this give us? It looks like negative 4 times 5, or negative 20. Maybe I'll write that y to the fourth next because it looks nice. So there's my negative 4 times 5. That's 20. It looks like we've got an x in there, so I'm going to write that. Then we've got our y to the fourth. I'm going to write that. And then I'm going to write our sine next. All right, and last but not least, let's do this, the grand finale. This one will actually, I think, be the easiest of them all. So now I'm treating, well, I mean, they're all pretty similar. So now I'm taking the derivative with respect to z, so the only variable I see is my z to the third. Well, okay, if I take the derivative, again, the 4 comes along. Chain rule, just like the same thing as before. The derivative of cosine is negative sine. I leave the inside stuff alone. So there's no derivative yet on that inside part, right? So the x and the y and the z, they all come along. But now, by the chain rule, I am taking the derivative of the inside stuff. Well, x times y to the fifth, that's just a constant. So when I take the derivative of that, that's just going to be 0 when I take the derivative. And the derivative of z to the third, well, that would be just 3z squared. And again, I think I left off a bracket up here. Okay, then I could just simplify. So it looks like negative 12. I've got my z squared, and there's my sine. Whew, and I think that would be, excuse me, all of the partial derivatives in this case. So I drew a picture too here, and notice my picture for a surface. This is just if we have a function of 2 variables. Okay, so a function of 2 variables is going to produce a 2-dimensional surface. So in this case, we would have a function of 3 variables. So in this case, our domain is actually going to be more of a, well, it'll be a solid. It'll be something in 3 dimensions. So my picture doesn't quite go with this situation, but my picture in terms of gradients and slopes, that would work if you have a function in 2 variables, x and y. Okay, oh my goodness. So, how is that? Does that work? So hopefully it does. Oh, I've got to do my random plug. Sorry. So if you want to help support, the best way is Patreon. And of course, it's just my name on there, Patrick JMT. I'm going to start trying to do these office hours a little more if people like them. This again is just very much an experiment. So you can, and this is not directed at you. Oh my gosh, this is any of you kind souls. So the lowest one is what? About 3 cents a day. So if you want to help a brother out, think about all those expensive frappuccinos. So, anyways, but also too, when I start doing more of these live streams, if I save notes and things, those all will be posted to Patreon. You can sign up to Patreon for free. You can just be a free viewing member, so you don't have to like sign up for some tier package or anything like that. But everything that I start linking, because I'm like when I do review sessions, I'm going to start uploading these I can upload these as PDFs. People seem to like them. So maybe not for office hours, but just anyway, anything that I have to relay will be out there. So, okay. So there is that. And I know there were some other questions. I just don't know if everyone is still there. So A and B for your second part, you should use Taylor's remainder theorem. And I would have to look over it honestly to bust it out real quick. But it's just, I forget the exact formula. I remember it pretty close. I think I've got a video on that. I don't know if somebody... Sorry, I want to look at one thing here to the side too. Somebody had this good question about, why is 0.9 repeating equal 1? I don't know if it's worth talking about. I'm trying to find with a nice proof that will convince people, because there's a bunch of different ones. Okay, good. Oh my gosh, I'm glad that it helped. I don't understand your question, A and B. The difference between 5 DC and 8 DC? I don't know. Oh, 5 decimal places and 8 decimal places. Like I said, I would have to dig out that formula. Let me see if I can find it. Right, so obviously you understand the question. It's just getting it to agree to a certain point. So you would need the error, right? So 1, 2, 3, 4, 5, 6, 7, 8. Right, so you would need the error to be smaller than what would be the best way to do this? Well, eventually you should get something that says the error is less than, and it should agree to the first 8 decimal places, which is what should happen, instead of 5. That should really be all that happens. It says the error should be something less than blah, 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 and we don't really care what's after that. So that would mean it agrees to the first 8 decimal places or the first 5 decimal places is really all you're looking for. So let me see. So okay, I'm sorry. I'm looking for a good simple proof that convinces me. I don't even know if it's worth doing. Yeah, so maybe this is I kind of like this explanation, so I think this one convinces people. This is always the one that I liked. Maybe this is a simple one. So there, and another question you can ask yourself is, What is the difference between, um, you know, 0.99 repeating and 1? How far apart are those two? Don't say it's 0.00000. Well, you can say that. Just keep going. 0.00000. One explanation I think everyone likes. So I would say, do you agree that 1/3 equals 0.3333 repeating? So that would be my first premise to ask someone. Do you agree with that? If someone wanted a proof, this would be probably one of my very most basic questions. So if so, well, if you agree that that's true, I'm pretty sure that you would agree that 1/3 plus 1/3 plus 1/3 equals 1, right? Most people would agree with that, right? A third plus a third plus a third is equal to 1. But if you agree that 1/3 is 0.333333, which it is, then you get 0.9 repeating, and it equals 1. That's it. So, ta-da! That would be one proof that you could show people. I think is it a little circular? I don't know. I don't think so. And again, what's the difference between those two numbers? It's 0. There's zero difference, right? Pick a number. It's smaller than that. That's the point. So people like to ask this misguided question, like what's the closest number to 1 that's not 1? Well, there's that question doesn't make sense. There's not one. Okay, yeah, I see your question, Nirban. Can you explain why integration and differentiation they're not reverse processes. We would say inverse processes is what we would say. We would say that they're more of inverse processes. Not you wouldn't want to use reverse. I think that's bad terminology. And I know it sounds nitpicky, but again, math is nitpicky, isn't it? So say that they're inverse processes. It means they kind of undo each other, is the idea. What's the good simple explanation? Because it's not really quite so simple. Let me see if I can give you a nice little succinct explanation. I'm trying to give you one that doesn't just say, something mechanical. It's kind of boring. And this is something that people didn't even, and I'm saying too, like, it's something like when they do the fundamental theorem of calculus, they kind of even just like glaze over it in a textbook. I mean, the basic idea, while they're inverse processes, I guess you could say, in a sense, just by the mechanics of taking a derivative, right, it just breaks down into a function into different functions. And integration, in effect, the way the process is set up, simply reverses that to get you back not quite to the original function, but the original function up to a constant. So you're pretty close. But again, you do get that constant, which is okay. I mean, to me, that would be the real, like, sort of vague, generic answer, but I don't know if that's satisfying to most people. Let's see. So I don't know if that is satisfying at all. Just sort of mechanically, that's how you would recognize that they're inverse processes. But again, historically, people didn't recognize this for a long time. It kind of felt like different people kind of knew about differentiation, and they kind of knew about this It was like derivatives and computing integrals. If you call it derivatives and integrals, it doesn't sound like they should go together, right? If you call it derivatives and antiderivatives, it's like the English clues you in, right? Those are clearly related. But maybe if somebody said, hey, these are derivatives and these are integrals, like you wouldn't immediately think they're related. You would think, okay, here's this and here's this. And people didn't, again, I didn't notice it at first. And of course, again, it really all comes from the fundamental theorem of calculus is the justification. I mean, that's the proof. So I don't know really how to give a proofy answer without just citing the fundamental theorem of calculus. Okay, I hope it helps. I mean, again, it's kind of hand wavy, right? I don't know if it's very satisfactory or not. But why? If you really want to know why, like really why, you just have to go understand the fundamental theorem of calculus. That's why. I mean, and again, it feels like a cop-out answer, but I'm just saying it's not trivial. So okay, I hope it does help. Oh my goodness. Alrighty, let's see. How are we doing? Any other questions? I may just go back to my own little work. There's a question that I wasn't able to solve. Can you help me with it? Maybe. I don't know. We can try. It depends on what it is. I am not the all-seeing guru. I may have to cheat and use computers and technology and books, but I kind of like this. Let's make it a team effort. So yeah, we can try. I'm trying to think what I have to do today. Most of my obligations are this afternoon. Yeah, Nirban, my pleasure. I always like to ask this question: where y'all from? It's interesting when I'm here in the mornings. I tend to get a lot of people overseas, particularly from India. I've noticed. Makes sense, right? Maybe just because of the time change. Everybody I know is in school or going to school soon. So, a value of b for which the equations have one common root in common. Okay, let's see if we can figure this out. Y'all can help me on this one. So, because I get stuck too. I'm not so clever. So see, I knew. India. Your all's names. Yemen. Oh, cool. Oh, Yemen. Okay. Sorry. I don't know if we're friends. I'm friends. I think anyways, maybe we should leave politics out of it. India. Okay, so see, I knew it. Okay, so we've got two functions. Y equals x squared plus bx minus 1, it looks like. And then we've got y equals Bay Area. Nice. I had somebody yesterday from Southern California. I've only been to LA once. I told the same person, that was a crazy time. That was a crazy experience. And then I've been to San Francisco at least twice, maybe 3 times, but it's gotten crazier too. Okay, I'm glad we're friends here. Okay, so maybe you all can help me with this. We want to find a value b for which these two equations have one root in common. So, how could we do this? Where am I from? I'm from the big state of Texas. Currently, I should say, at least I live in Texas. So that's not where I was born, but that's where I live. So how would we get started on this? So the idea is, right, we've got, and if we're setting something equal to 0, right, so we're trying to find these solutions. I like these questions because they're a little more generic. So we want to solve this. I'm already looking at one way to do it. In fact, I think I've got getting better, but not any cheaper. Yeah, I hear that, brother. I assume brother. Shamar sounds like a guy's name. My apologies if it's not. Um, so yeah, I don't know how people afford to live in California. It looks beautiful. Obviously, that's why people want to be there. But okay, so can we make it to equal to each other? I think would that work? Well, we want them to both equal 0, so that seems reasonable. Okay, so now what could we do? Or a system of equations, yeah, right? The little brackets even suggests a system of equations. Douglas, hey, how are you? Good to see you again. So let's see, what would we have here? I think we've almost got it at this case, right? Because we could subtract x squared from both sides. We could have bx minus x. So if I subtract x from both sides, and if I also subtract b from both sides, it looks like we would get that. Maybe that's not even what I want to do. Let's do one other thing. Let's just put our x's on one side, right, and our constants on the other. So I've got bx minus x, and then I've got b plus 1. So to me, this is now just a linear equation that we're solving. See, I remember you, Douglas. Douglas was our friend from Florida, so I was speaking about. So in this case, we've now got a linear equation. Does anything weird happen here? I don't think so. So again, b is just a number, so I think we could factor the x out on the left. And it looks like if we divide both sides, it looks like that would be our value. And someone could double check this, but I think, and this is again, obviously, b couldn't equal 1. Which makes sense, right? Katie, that's right. I'm sorry, you were from Katie. I knew it was close, not Florida. Katie, you're my neighbor. You're my Texas neighbor. And notice it makes sense that b doesn't work. That makes sense because what would we get? We would have the equation x squared plus x minus 1 equals 0. But then we would have also the equation x squared plus x plus 1 equals 0. And there's no way this can have a solution. No way, Jose. Right? There's no way that equation could have, that system of equations could have solutions. Because whatever you plug in for x, right, in this portion, you're going to get the same number in each one. Well, if I add 1 to that quantity and it gives me 0, I couldn't take that same quantity, what did I say? If I take that quantity and subtract 1 and get 0, I couldn't take that same quantity and add 1 and get 0. So there's no way that would have a solution, and that's what this is telling us. So that makes sense. So yeah, it just looks like, and now does this work? I guess this would work for any b value, right? That's the interesting part. What am I doing here? Am I losing my mind here? I think we're okay. I think I'm losing my mind. Okay. With that, okay. Now I'm thinking for a second, sorry. Does it seem counterintuitive to think about the fact that the harmonic series does not converge? No. What was the harmonic series, right? What is it? 1 plus a half plus a third plus a fourth. It's that one, right? That's the harmonic series. I should remember this. I mean, because you're adding up infinitely many things, right? And you can add up infinitely many things and it not get, small enough to add up to a finite number. So that's certainly possible. So that doesn't bother me. But no, and there's a pretty easy, right? There's a pretty easy way to show that this doesn't converge. So So how do we show that this does not converge? Sorry, I'm thinking about something else over here now. And for those of you all that maybe don't know about convergence, or to converge or diverge, it means if you add them all up, you get a finite number. And to diverge means you add them all up, and you get not a finite number, is basically what happens. It doesn't have to go to infinity or positive infinity. It could oscillate, for example. So we have to be careful about exactly what we say in that case. So one way you could show that this doesn't, well, maybe I'll even give you all a second, since we're just doing office hours here. And maybe an example of one that does converge, and this is the one I always use. Maybe it's the one we could even use a second ago, right? I could take 0.9 plus 0.9 plus 0.009 plus, right? I'm still adding up infinitely many things. It just so happens they're getting smaller and smaller and smaller. And if I add those up, I would get 0.9999 repeating. So here, if I'm adding all of those up, here if I add all of those infinitely many numbers up, I'm going to get 0.9 repeating or 1. Yes, sequences and series tend to give people a lot of issues for sure. Okay, so that's an example of a convergent series. Now the idea is, though, if you think about 1 plus a half, I'm going to write out just a few extra terms. I remember I was happy because I remember, when we had to take a pre-calculus, when I took a calculus class, the instructor was like, does this converge or diverge? And I immediately saw the answer and I immediately saw why. And it's not complicated, but I just remember no one else got it, or at least no one else seemed to have got it. So the teacher was really happy that I caught it really quickly. So I'm going to claim this just goes off to infinity. And again, infinity is not a number. It just means it gets arbitrarily large. So, okay, if you think about 1 plus, okay, so then I'm adding a half, 0.5. Let's look at the next two numbers. I'm going to look at the next two numbers, and then I'm going to look at the next 4 numbers, and then I would look at the next 8 numbers, and I would keep this up. 8 numbers, etc. Now, if I look at 1/3 plus 1/4, so 1/3 plus 1/4. Can I say that this is bigger than some value? Is there something that's clearly larger than? There's a lot of ways to prove lots of things in general. So yes, there's certainly ways to do trig identities without geometry, but I mean, trig is rooted in geometry, so that's certainly the natural way to do it. So if you think about a third plus a fourth, right? A third is bigger than a fourth. I mean, if it was a fourth plus a fourth, we would get a half. But since it's a third plus a fourth, we know that those together are going to be larger than a half. So I've got 1 plus a half, and this is going to be something larger than 1/2. And if I look at the next four numbers, right, a fifth plus a sixth plus a seventh plus an eighth, well, this number is larger than 1/8. A sixth is also larger than 1/8. A seventh is also larger than 1/8. So if we add all of these numbers together, again, it's going to be larger than 1/2. And if I go to the next 8 numbers as well, again, I'm going to add something that's larger than 1/2. And then I'll go to the next 16 numbers, and again, I'm going to add something that's larger than a 1/2. And that's the fun part, right? You're going to need more and more terms as you go out, but you've got infinitely many to play with, so it doesn't really matter. You can always add up, you can always find you can always look at the next chunk of numbers, add up enough of them, and get something that's larger than 1/2. Well, then you go to the next chunk. You can do that again. So you're in essence showing that you've got 1 plus something larger than a half, plus something larger than a half, plus something larger than a half, right? So if you keep doing that, clearly it's going to go off. It's not going to add up to something finite. So that's kind of, I think, that to me is the clear, that's, well, at least I guess I was going to say it's the clearest, most intuitive one, because that's the one that I, came up with in my calculus class 20 some odd years ago. So yeah, I think that's a nice basic one. And I like this stuff, sequences and series and all this, because yeah, to add, right, you want to add up stuff, and it's got to be, yeah, right, there's no memorizing, right? It's just like, I could explain that to a child. I mean, and I don't say that in a derogatory way at all about anyone watching or myself. Again, that's the one I came up with. That's what's nice about it. It's so simple, right? There's nothing, harmonic series, that sounds so crazy. But yeah, it's pretty straightforward. So there it is. But yeah, that's what I like about series. It's like, okay, you're adding up infinitely many things. They have to be getting smaller. They have to be getting smaller, and that's sort of the question. Are they getting small enough, fast enough to add up to something finite? In the harmonic series, those numbers are getting smaller, but they're not getting small enough fast enough. But in our other example, like the 0.9, 0.09, those numbers are getting small enough, fast enough, so that they do converge. And just for fun, do you all remember what this other type of series is called? So what type of series is this one? So I don't know, for those of you that have done series, and these the one that I'm asking about here, that's something that you would see, at least here, I would certainly talk about it in a pre-calculus course. Yeah, perfect. Very good. Yeah, this is just a geometric series. So this is definitely one of those series, right, that in a math class you would be expected to recognize. I would, at least at some point. Yeah, so we would say, yeah, that's fine. We would say it's a series in this case because we're adding them up. And again, a series implies adding up things. So, and again, you could write this as, right, 9/10 plus 9 over 100 plus 9 over 1,000. And recall, in this case, our ratio that you're multiplying by to get to the next number, our common ratio. In this case, our common ratio would be equal to 1/10. And recall that if the absolute value of our R value is less than 1, if that ratio is in between, not including -1 and +1, it converges. And it converges to the first term over 1 minus that common ratio. And in this case, our first term was 9/10. That's just the number we were given. And if you do 1 minus that ratio of 1/10, you'll get 9/10 over 9/10, which again is what, we get equal to 1. So just another little random tidbit on series. Okie dokie. So there it is. Okay. What time is it? It's almost an hour. I'm going to take a little break. And I'll be back soon. Because it is hot here in Texas. And all my poor plants are just withering and dying out there in the sun, despite me trying to water them. I am not an artist, but we'll try. All right, friends. Sorry, I'm just like entertaining myself now. Okay, so I'm gonna go water some plants, and then I shall return. If people have questions, feel free to do whatever. Help each other if you want to. All right, I'll be back, my friends.